A freight train carrying 10,000 tons of steel, coal, or grain across the country once required a crew of 5 men to operate safely. Today, it runs with 2. The only difference is a 5-pound aluminum box bolted to the last car. Why would something you could buy for a few $100s make an entire vehicle and an entire profession disappear? Why did it take until 1990 to figure that out? The easy version of this story is that technology replaced the caboose. Railroads got smarter sensors, better radios, computerized dispatch, and at some point, they didn't need a rolling cabin at the back of the train anymore. That's true, but it skips the part that actually makes this interesting. The caboose wasn't riding at the back of the train for comfort. It wasn't a tradition. It wasn't there because someone decided crew members needed a nice place to sit. It was there because without human eyes at the rear of a moving freight train, the train would destroy itself. And for about 130 years, nobody had found a better solution. The history of the caboose is really the history of a problem called the hotbox. And the hotbox is where this story actually begins. Before the mid-20th century, every freight car in North America ran on what were called plain bearings, also known as journal bearings. The axle of each car sat inside a metal box packed with oil-soaked cotton waste. That packing was the only thing keeping the steel axle from grinding directly against the truck frame. When it worked fine. When it dried out, or when the oil leaked, or when the packing got contaminated with grit, the friction built fast. The axle would heat up, the box would smoke, and if nobody caught it in time, the bearing would fail completely. When a bearing failed at speed, the axle end could literally burn off. The car would drop, the truck assembly would collapse, and a derailment followed. On a train moving at 50 miles per hour through open country, that meant a pile of wreckage spread across a quarter-mile of track. This happened regularly, not occasionally. Regularly. The only way to catch a hotbox before it became a derailment was to see it or smell it while the train was moving. Smoke coming off a journal box, the faint chemical smell of burning cotton, a faint orange glow at night. These were the signals, and the only people positioned to catch them were the men riding at the back of the train, in the caboose, looking forward along the length of the cars. The conductor and the brakeman sat in the cupola, the raised glass booth on the roof of the caboose, and they watched. Every mile, every hour, in daylight, in rain, through mountain passes at midnight. They were looking for smoke, shifting loads, dragging equipment, brake shoes that hadn't released properly, and cargo that had moved and was about to fall. The cupola existed for exactly this purpose. It wasn't a perk. It was a watchtower. They also handled the paperwork. Freight trains in this era were complicated, logistical operations. Cars got picked up and set out at intermediate stops. Manifests had to be updated. Switch lists had to be tracked. The conductor ran the business of the train from the caboose, while the engineer ran the machine from the locomotive. The two ends of the train operated almost like separate departments, and when the train stopped on the main line, the rear brakeman climbed out and walked back down the track with a red flag or a lit fuse to protect the rear of the train from any following traffic. In territory without signal systems, this was the only thing standing between a stopped train and a collision. So the caboose wasn't nostalgia. It was load-bearing infrastructure. It carried people who were doing jobs that couldn't be done from anywhere else on the train. The question is what it took to make all of those jobs disappear. 4 separate technologies had to converge, and none of them arrived at the same time. The first was the roller bearing. Starting after World War II, freight car manufacturers began replacing plain journal bearings with sealed roller bearings. A roller bearing doesn't depend on oil-soaked packing. It's a precision-machined assembly of steel rollers inside a sealed housing with its own lubrication, designed to run for hundreds of thousands of miles without a tension. The hotbox problem didn't vanish overnight, but the frequency dropped sharply. By the 1970s, most new freight cars were being built with roller bearings as standard. The second technology was the wayside defect detector. Beginning in the mid-1950s, railroads started installing infrared sensors alongside the tracks at intervals of 20 to 30 miles. As a train passed over one of these detectors, sensors aimed upward at the underside of each car measured the heat radiating from every bearing on every axle. If any bearing exceeded the safe temperature threshold, the detector flagged it. Early versions tripped a signal or notified the dispatcher by wire. Later versions broadcast directly to the crew by radio. Train number, track, axle count, and which specific axle was running hot. The crew no longer needed eyes on the rear of the train to know if something was overheating. The track itself was watching. The third was centralized traffic control. CTC is the system by which a single dispatcher, sitting at a console hundreds of miles away, can control every signal and every powered switch across an entire subdivision. Before CTC, a brakeman at the rear of the train had to physically climb off and throw switches by hand when the train needed to move onto a siding or a branch. After CTC, that switch was thrown remotely before the train arrived. Combine that with handheld radios that let the engineer and conductor communicate in real time, and the rear brakeman's operational role on a road train largely evaporated. That left the safety monitoring function. The eyes in the cupola. The fourth technology handled that. It's a device about the size and shape of a small car battery, and it clips onto the coupler at the rear of the last car in the train. Railroaders call it a FRED, flashing rear end device. The official name is End of Train Device, or ETD. It does several things at once. It monitors the brake pipe air pressure at the rear of the train and transmits that reading via radio telemetry to a receiver in the locomotive cab, called the Wilma, every few seconds. The engineer can see at any moment whether full braking pressure is reaching the last car. It has a motion sensor that can detect if the rear of the train has separated from the rest, and it has a flashing red light that marks the end of the train to any following traffic, the same job that was previously done by the red lanterns hung on the back of the caboose. Florida East Coast Railway started using FREDs in 1969. They were running freight trains without cabooses, while every other Class 1 railroad in North America still had full rear-end crews. It was a live experiment, and the industry watched it for years before following. The transition wasn't clean. The first generation of FREDs could monitor brake pressure, but they couldn't do anything about it. They were passive instruments. They read the pressure and reported it. When the pressure was wrong, the engineer at the front of the train had to respond. And on a train a mile long going down a steep grade, response time matters. The problem showed up on mountain railroads. When a train descends a long grade, the engineer applies the brakes by reducing air pressure in the brake pipe. That pressure change travels through the train as a wave, from front to back, and the brakes apply in sequence. On a train with a caboose, the rear crew could apply emergency braking from their end if something went wrong mid-train. Without the caboose, that backup was gone. On steep grades in cold weather, moisture could freeze in the brake line and block the pressure signal partway down the train. The brakes at the rear of the train wouldn't apply. The engineer reading his gauges at the front might not know immediately. On a downgrade, that situation could escalate into a runaway within minutes. There were accidents. The Federal Railroad Administration stepped in and mandated a redesign. The second-generation FRED became a two-way device. Now, the engineer could transmit a command to the FRED, and the FRED would open a valve at the rear of the train and dump the air from the brake pipe, putting the entire rear half of the train into emergency braking. This is called the DPS function, Dynamic Positioning System, and it meant the engineer now had active control of the rear of the train for the first time in the history of railroading. In some ways, the smart FRED gave the engineer more information and more capability than the rear-end crew had ever had. But getting there cost something, and the industry moved faster than the engineering was ready for. The labor displacement was enormous. A standard freight train in the 1970s might carry an engineer, a fireman, a conductor, and 2 brakemen. 5 people. After the FRED became mandatory and the unions negotiated the terms of the transition through the 1980s, that number dropped to 2, engineer and conductor. The Brotherhood of Railroad Brakemen effectively ceased to exist as a meaningful occupation. The 1980 Staggers Rail Act had deregulated the industry and given railroads the pricing flexibility to survive, but it also gave them enormous pressure to cut costs. The caboose and its crew were the most visible line item. Virginia held out the longest. The state had a law on the books since 1911 requiring a caboose on every freight train. It stayed on the books until 1988. When it was finally repealed, the last legal holdout was gone, and the transition that had been happening in slow motion for 2 decades finished in a matter of years. By 1990, cabooses had been pulled from mainline service across North America. There are still a few places where cabooses show up. Trains carrying hazardous materials sometimes use them because regulations require a crew member at the rear to watch for leaks or spills. Local freight jobs on industrial spurs use them when a train has to make a long reverse movement, and someone needs to stand at the back end to watch the track ahead. On those moves, a Fred is useless. It can't see. It can only measure. And in those specific situations, the old problem reasserts itself. You need a human being at the back of the train with eyes on what's coming. That tension is worth sitting with. The Fred replaced the caboose crew for 99% of what freight railroading involves. But that remaining 1% still requires a person. And when that situation comes up, railroads either put someone on the rear platform of the last car, or they dig out an old caboose. There are a few hundred still in active service in North America, mostly on short lines and regional carriers. They look exactly like they did in 1965. What the caboose story really tracks is the shape of how industrial automation works in practice. It doesn't replace everything at once. It replaces specific functions, one at a time, as the technology to replace each function becomes available and economically viable. The hotbox detector made the lookout obsolete. CTC made the rear brakeman on a road train obsolete. The Fred made the brake monitor obsolete. Each piece of technology arrived separately, over 40 years, and together they dismantled a job that had existed for 130 years. The crews who rode those cabooses weren't doing redundant work. They were doing work that was genuinely necessary, given the tools available at the time. When better tools arrived, the work changed. That's the honest version of the story. The 5-pound box on the back of the last car is transmitting brake pressure data to the cab right now on every freight train rolling across the country. Nobody's watching from a cupola. Nobody's smelling for hot boxes or checking the manifests at a desk bolted to the wall. The train is longer than it has ever been, sometimes stretching past 1.5 miles, carrying more tonnage than the engineers who designed the first cabooses could have imagined. And at the very end of it, a red light blinks every second into the dark, marking where the train ends and the empty track begins.